working, right?
Yes. Okay. I'll be back.
All right. So last time we finished 5.2, and the topic was the definite integral. And again, we didn't see any special way of finding integrals except two ways. One is to use limit of a Riemann sum. That's where you have to find delta x, you have to find x of I. And then you have to substitute this into limit of a sum, and then going through the process of simplifying, you're using formulas for I, the list of formulas that I gave you, and we're trying to find the limit. Now, it's the process that we had, it's kind of straightforward. It goes into the concept, but it's very time consuming. And that's one thing. The other thing is, if function is complicated, not simple function, even like, for example, if we go just with trig functions like sine, cosine, it will be very difficult to find those limits when we substitute in, lots of simplifying. So it's not the most efficient way of doing it, but that's how it was developed. The second method that we had is using areas. Remember, evaluate integral in terms of areas. So that means we graph the function, look at the picture. If it looks to you like you can use formulas from geometry, for example, you see a circle, you think about pi r squared, right, and then maybe divide by 2 or 3 or whatever, let's say, general idea. And also, if you have triangles, then use formula for the area of triangle, right? If it looks like trapezoid to you, then you can break it right into pieces. You can have a rectangle and a triangle. But even by graphing, it still doesn't work for every function, because some functions will not have any lines in them, or semicircles or circles. So those methods are good, but they are limited. So we have to achieve another way or find another goal how to find those integrals. And that's exactly what we'll be doing today. In the past, when I say past, it's not yesterday, okay? In the past, hundreds of years ago, when the calculus as a separate subject was developed, this was a very big problem. Mathematicians knew that they have differentiation, so derivatives, and they understood what those are, like we said, slope of a tangent line, right? Or any rate of change that we're talking about, velocity maybe, or maybe acceleration if it's a second derivative. Those things were connected, okay. But then we have the separate subject, let's say, our topic, as integration. And the idea of area under the curve was developed okay overall. They understood what they were looking for with these methods, let's say. And also distance. You have a couple of problems with the distances there on 5.1, I believe. But they couldn't connect derivatives and integrals. But then it happened, and that helped us actually to know how to find integrals of more complicated functions. And that's what we'll be talking about today. So for section 5.3, I think we have to break this into 2 lessons because it kind of will be lengthy a little bit. So we call it the fundamental.
Is he in here? He went to his room.
Okay. I'll turn on just a second. Let me finish writing this. Okay. So where's my note? All right, so we have the fundamental theorem of calculus.
That's not important.
Overall, yeah, sounds important. That's right. It's it's important. I don't know what else to say.
It's fundamental. Why did we move this first?
But, because you were not ready. You had to grow up a little bit, okay? In mathematical terms, okay? To get to this. No, but overall we have 2 of them, not just 1. We have 2 of them. And we have to be careful not to go too fast here. But actually the second one will help us to get the method and the idea how to find integrals. The first one is like a precursor for the second one, but we cannot just bypass it. So first let's talk about a couple things that we need to know and understand So let's put a little sketch over here. So let's say we have a function, and this function will be on interval a and b like we had before. So we understand that if we are looking for the area under this curve, y equals f of x, well, that will be the area, and it's just the integral from a to b f of x dx. And this is what last time we called definite integral. Why? Because it's a number. When you calculate using either method, let's say, or any method, you'll get a number. So that's why we call it definite integral. But for the general purpose, it's not the best what we can do overall in calculus. Because we want to be more flexible, not just to say, well, this is what we have, this is the area, and nothing happens. Okay? What we're trying to do, we're trying to find some way out where we will talk about functions. Because what if we have functions that describe the area? So this is what we have to look at. So for example, let's take a look. Let's say somewhere over here I'm going to put x. And this x is not a constant, or some number. This x is the variable. Now what that does to me, or for the problem, that if you say, okay, I'm looking for this piece over here, it still will be defining the area. This is the area, it doesn't go anywhere. But the problem is now that this area is not a constant as a number. Why? Because remember, x is what? The variable, right? So what that means, x can change anytime. You know, I can take this x and move it to the right. Now area will be larger, right? If I move this x to the left, area will be smaller. So if you follow the same idea, the same thought processing, then you will realize if x is the variable, then the area that we will be talking about over here is not a number. What area will be here, it's a function. X is the variable, area is the function. X is a number, like a and b, second, then we have a number, okay? So what here will create a function which is g of x, for example. And this g of x is, again, the area, but not a number. It's a function. So what is g of x? G of x actually is the integral. Again, don't forget, integral describes the area. From a to what?
X.
Good. And inside, you have your function, but you have to be very careful. It's not f of x dx. It's everything but f of x dx. And of course, you cannot use a and b. So normally we put f of t dt. We cannot use x, okay, right now at this moment, because x only is changing, x is only used for what? For the upper limit, right? X will change over here. But here we have a function. So what are you looking at? You're looking at g of x, which is the integral, but at the same time it's not a number, it's a function. But still the area. Do you understand this? Okay? So, make sure you understand. X is changing, area is changing. So it's not going to be a number. It's just a function that describes what that area is. So if you know like x is 5, you will take this 5, substitute into the function, and you know what you have as a number for that specific x. But overall, x is the variable. So don't forget that. X is the variable. So this function right now describes the area, and area is changing. Now what's unusual here maybe, that your upper limit is the variable. Now later on when we finish today, you will see it doesn't have to be just tiny little x. You can throw in here anything that you want. For example, you can call this x squared plus 2x minus 5. This whole thing can be a long expression. Or you can call this as a natural log of x. All of these things can change. Your upper limits, upper and lower limits, they don't have to be numbers in general terms. We'd like to deal with a certain interval, okay, because that's the idea of the area. But as a big concept for calculus, they don't have to be numbers. They can be variables. You can change your interval, you can move it, change it, shrink it, whatever you want to do. So that's the idea just for the function. But now let's see how that fundamental theorem of calculus 1 will work for us. So, fundamental theorem of calculus 1. So as I told you, we have two of them. And the first one still will not tell us how to find the area, but will help us to work with the next theorem. So here's what we say. We say this. If f is continuous on closed interval AB, and this is very important, if your function is discontinuous on this interval, then we have a problem. Okay? We want to make sure that this function is continuous on this interval. Then the function g defined by g of x equals integral from a to x f of t dt on the same interval is continuous on this interval AB, closed interval AB, and differentiable on open interval AB, and very important conclusion, and, because this is what we'll be working with, and g prime of x, meaning what? I'm going to take derivative of this function, okay? And g prime of x equals f of x. Okay? So finish writing, we'll talk about what that really is and how this can be applied and what can we do with this. Alright, so let's look at little pieces, parts. So when we talk about f is continuous, we know this f is inside, right, of integral. And we're trying to connect these two functions. Function which sits inside and function which sits outside. That's our idea right here, is to connect them. Again, f has to be continuous on closed interval. Then we know that the function g of x, which is the integral of f function on a to x interval, so it's changing, don't forget. This function will be continuous. This function will be differentiable. That means I can take the derivative, and if I take the derivative, what do I get?
G prime of x.
I get my what? Inner function. So what you're trying to do, you're trying to talk to the function, you're trying to connect them, and you're trying to see how this can be done. How can you take the derivative of something that has integral and all of those things? And we actually had this before. That was in chapter 4 at the end. What do you think the connection between them? There's one word that we have to say, and that's it. What do you see? Especially if we're paying attention to this.
Derivative. Derivative.
Not exactly.
Antiderivative.
Antiderivative. That's right. Okay? If we look carefully, it's actually antiderivative. So what we're doing here, we're touching concept of antiderivative. And if you understand what antiderivative is, then you can actually find any integral. That's the missing link that I told you for many centuries we couldn't put this together. But when they realized that actually g of x is antiderivative of f of x by looking at this, then basically everything changed. So what we are saying, now knowing what antiderivative is, we can't find any integral. I already said this, I'll repeat this many times. So by looking at this, we know that g of x is antiderivative of what? F. Okay? So, and this will be more visible in the second theorem, but this one has to be done, okay? So let's see how this can be done. Now, first of all, let me put this way. I'm going to add a couple of things, maybe this will help you to understand. Now, this only works at this moment, only when you have x as your upper limit. Do you understand? If you put from a to b, that's not going to happen right away. It's not. It's only when we have x on the top, or at least some function that has x, meaning what? The expression. Okay? That's what we have. The other thing, what you should realize here, that derivative and antiderivative, we already talked about this, but here it's even better to see that antiderivative, for example, and the derivative, they are like inverses, right? Going opposite directions, yes? But when we say inverses, what that means, they can cancel each other. Look, if I'm going to take derivative of this one, and my answer is what? Whatever sits inside, right? That means what? This will be gone. Remember you had this in trig when you were saying, when I have my function, let's say sine of x, and I apply the inverse sign to this function, what's the answer? The answer, so these, right, opposites, and they will be canceled, and what's left, just x, right? Well, the same story is here. When you take the derivative of this, again, not forgetting any x here, or anything with x, when you apply the derivative to this, derivative will cancel the integral, and you will have just your function inside. Of course, it will be function of x instead. It will be function of x. So derivative can cancel integral, and integral can cancel the derivative. But we'll talk about that more next time, okay? So let's take a look at a couple examples how this can be done with the first theorem using this concept. And you will see this, these examples that are related to this first theorem, very simple, but we just need to know the procedure. So let's take a look at the first example. So we have function g of x as the integral from 0 to x, square root of 1 plus t squared dt. All right? That's what we have. The next question, we need to find g prime of x. So here's my simple question. What is g prime of x? Based on the theorem.
The derivative of 1 plus t squared?
No. Take a look at the theorem. Take a look again. You're almost there. What does it say? The conclusion. The g prime of x equals f of x, right? Well, what that means. Here's your f function, right? But it says f of x. So what's the answer?
Square root of 1 plus x squared?
Square root of 1 plus x squared, and you're done. That's all you have. Now, again, using, right? I'll put use fundamental theorem of calculus 1. So overall, what we have to do, if this fits nicely into the theorem, then what you have to do, you just have to pull out the function from inside and change the variables, right? Substitute, let's say. And that's all we have. Do you understand? That's all we have. Let's do one more. Let's say we have g of x, and we have integral from x to 1 sine of square root of t dt. And we still have to find g prime of x. So first thing, look at the theorem, look at my problem. Do you see the difference? What's different? X is where it's sitting where? X is sitting where? On the bottom, right? The theorem is not going to work. X has to be on the top. How can we do this? Right, we go back to yesterday's lesson, we used the property. And property said that you can flip upper and lower limits, but you have to put negative, right? And we have sine square root of t dt. Do you understand? We have to fit this into theorem. You cannot just decide, well, you have x and that's it. X must be on the top. Well, and that's all you need. It's going to work. So now we go with g prime of x. And what is the answer? Negative sine square root of x. And you're done. Okay? So what you're doing here, you're actually pulling out the original function. Okay? Pulling out the original function, whatever we have to graph to get the area. So that's this. So one more time, the theorem says from a to x, right? We want to see a from a to x. Now the other thing is what we really have to pay attention, the function is continuous. Okay? Well, these functions are continuous from one end to the other. So, third one, let's say we have something like this. Y equals, we can change the name, it doesn't have to be g of x all the time. Y equals integral from 0 to x to the 4th cosine squared of theta d theta. Okay, so what's different this time? X to the 4th. Okay, well, and at least I have a 0 on the bottom as a number, right? X is on the top. So I'm going to make this simple for you because what book does, which is right, okay, but then we'll come to conclusion and we're going to use the conclusion. Book is saying that but in this form, when you don't have x over here, just x by itself, you cannot do it. It has to be x. So what they are doing, they're doing substitution. They say this, well, let's call x to the 4th as z. So now you will have z, and theorem can be applied, but there's some other things that they must be done. So we're not going to look into this unless you really want or get to the ebook or just the book and see how they did this. I'm going to explain how we're supposed to do this as a process, and that will be enough. So first of all, checking where you have x on the top, on the bottom, flipping if you have to. Okay, next. The next step is what we had before. We're going to take this x to the 4th and we'll substitute into the function. So we'll have cosine squared of what? X to the 4th. But then, as a conclusion to which they arrive, they say this. And then you have to multiply this, not just, okay, we're done. No, we're not done. And then you have to multiply this by the derivative of x to the third, which will be what?
4x to the third.
4x to the third. And this will be the answer. Well, if you want to put 4 in front, let's say 4x cubed cosine squared of x to the 4. Okay? But I wouldn't simplify anything, change the form. So one more time. If it's not x, you're still going to substitute. But then you have to multiply this by the derivative of whatever you have on the top. If it's not x. It has to be x. That's it. Okay? Are you going to remember this? If you actually even go back to number 1, if you think about this, look. Let's pay attention quickly. So for number 1, what do? We actually what? Substitute, right? But could I say times by derivative of x? What is the derivative of x? 1. Okay, so you can actually think about derivative all the time. You substitute and take derivative of x, or whatever you have. You understand that? You can always think about derivative. Here we didn't do it because x and derivative of x is 1. But if you want to kind of get consistent, saying I substitute and take the derivative, feel free to do it. That's not the problem. Okay? So let me do one more. So let's say we have g of x equals integral from 1 to negative x tangent t dt. Okay? So it fits into the theorem, right? At least we have the right integral. The number is on the bottom. So we can take the derivative and we will have tangent of what? Negative x, right? And times, I'm already telling you, you cannot stop, okay? Times by 1. Times by negative 1. Alright, now ask this question in every class, every calculus today. Can we simplify more? And I put equal sign, meaning yes. So tell me what that is. What is tangent of negative x times by negative 1?
Would this be tangent of x?
Okay, tell me why.
Because tangent is one of those functions where you can do that.
Can you do that? Alright, well, and the answer was right. So what we have to remember here, we have to remember that tangent is the even, actually the odd function.
That's what I was looking for.
Good, I helped. So the tangent is the odd function. Now what that means that you can pull this negative from negative x, you can pull it outside. So this will be negative tangent of x. Okay? That's according to your trig class or pre-calculus class. Okay? This is not that you're supposed to learn in this class. It's like given, you should know this. And still here we'll multiply by negative 1. So as the end result, we'll get just tangent of x. Okay? So, let me do a little review.
Excuse me, announcement. At this time, we have a club president's meeting in room 300.
Okay, so, what about even and odd? Okay, as the idea. Let me refresh this because we're going to use this, let's say, I think on Friday. Okay, we're going to use this on Friday. So let's take a look. So, when we talk about even function, overall, the even function will have reflection about the y-axis. So, the simplest example we can think about is our parabola. Okay, so if you rotate this about y-axis, you'll get the same shape. Okay, reflection. You get the same shape. But the best, if you can think about this a bit in different form. For example, if this point is x, y, if you reflect, what do you get right here?
Negative xy.
You get negative x, y. Now what that means, it means if you substitute negative x inside of your function, so for example, if it's x squared, right? So let's say this, if you put x, you get x squared. But when you substitute negative x right here, what do you get? You get negative x what? Squared, right? It will be exactly the same as the original one. That's why you get that y. You understand? So when you substitute this into the function negative x, you'll get the same thing back. What really fits into this is our cosine function. Cosine function is even function. Remember how it goes near, let's say, or close to y-axis? Remember how it goes? It intersects at what? Y equals 1, right? And it goes this direction. So it has symmetry, okay, about the y-axis. Now, when we think about, for example, odd function, so odd function has symmetry about the what? Origin. So, for example, we'll get something like this. That's what we'll call symmetry about the origin. So if my point is over here, which is x, y, well, the symmetrical point will be over here somewhere, right? And this will be what? Negative x and negative y, right? So basically what that means, if you substitute negative x into your function as the result, you will get your function, but it will be what? Negative function. Okay? So this one is even function. This one is odd function. So what I'm saying, let me repeat again, maybe this you will remember. In pre-calculus or trig, or 143, depends what class you took before, you should learn this. If you take negative x and substitute into your function, you will get f of x. And this is what we call even function. So basically what we say, you put negative x, you simplify, and now you're looking at its original function. Came back to you. You understand that? That's what we're really saying here. Then, if we talk about odd function, you also will substitute negative x. But as the end result, what do we get? We get negative f of x. So it's still your function, right? But it's what? Negative. So normally when we do this, we will substitute negative x, we will simplify, and then we'll try to factor out negative 1, and then whatever left inside should be our original function. Okay? That's what we're talking about. So going back to tangent, I mean, it should be as a fact that tangent function is negative tangent of x as what? Odd function. Remember I had the graph of tangent function? It kind of looks like this, except we have what? Vertical asymptotes, right? So it goes to the origin and has a symmetry about the origin, okay? But if you want to prove this, well, you know, and this maybe will help you a little bit, that tangent is what? Sine over what? Cosine, right? But what do we know? We know that sine is odd, which is what? Negative sine of x. You understand that? But we know that cosine is what? Even, so it's just what? Cosine of x. Well, what do you see here? Negative, right? Tangent of x. So again, why I was doing this, explaining this to you, because we will use this concept in the future when we start looking for integrals. So that's not something just to impress, but also to help us in the future. So, okay, you saw these 4 examples. Do you have any questions with these examples? Okay, so let me show you the most difficult one with this concept, okay? The most difficult one. So this will be number 5, right? 5? Yeah. Okay. So what we have here is this. We have f of x function. And again, remember, name really doesn't make any difference here. But then look what we have. We have integral, and let's pay attention to upper and lower limit. All right? question here is to find f prime of x. So it's kind of similar to what we had before. But what is different?
Both things have x.
Right. If you look at upper lower limit, they have x's, right? And that means you cannot use theorem. But question, can you modify your function that you can use the theorem? What do we need in the theorem? So if you look at that integral, what do we need in the theorem? Can you tell?
X.
Well, you already have x's, right? So that's not the problem. But what do we need? You need an a, right? The number. Can somehow you get that number? What can you do to get the number into the integral? What do you think you can do?
If you multiply on both on top and the bottom.
Well, you cannot multiply. But you can do something with one of the properties that we had last time. We had one property yesterday that you can actually apply and you will have it. Kind of scan through the properties. I want you to find it. See if you can find it, but I want you to find it. What do you think?
Yeah.
The A to C and C to B plus.
That's right, that's the one, right. What you're going to do, you're going to split the integral. So what are you going to do out of this one integral? You're going to create two integrals because you want to have number inside. Okay? Now the question normally I get here, okay, splitting, we understand what splitting, and that was what, number 2 property, kind of like if you count? So if you look at the papers, find number 2, and that was like it was said before, integral from A to C plus integral from C to B, right? So we can split. The question is here, as I said, normally I get like, what number should I put? What do you think? You're going to split this, right? So you're going to split this like this. Integral from square root of x, well, that's pudding, right? And you get arc tangent of t dt. And then you're going to have integral from, right? These two will be the same, yes, no? And then you get 2x arc tangent of t dt. So the question is, what do I put right here? And the answer is very simple. It doesn't make a difference. As long if the first line of your theorem can work. What does it say? If you go back to the theorem, what does it say about f?
It says that it has to be in between, right?
Well, but no, what I'm saying today's theorem. Fundamental theorem calculus, the first one today. What does it say? F is what? F is continuous, right. So you don't care what you're going to put in. You can put 0 if you like. You can put 1. You can put 2. You can put 3. Whatever. As long as this will not make that function discontinuous. Okay? Since this is arctangent, what do you know about domain of arctangent? Do you remember how it looks like?
So, all real numbers, right?
It will be all real numbers because you're. Let me see where I have it. So remember we said it's a tangent, right? Our tangent is inverse to it.
So it's pretty much the same thing, but sideways?
It will be on the side, but not exactly. Well, I can't do this unless I flip it like this. I don't know if you can still see it.
Yeah, like
Right here, right? Kind of like this. And you have a horizontal line. Asymptotes. But overall domain is what? All real numbers. So it really doesn't make a difference what number you put. Okay?
Just do 0.
You like 0, put 0. I put 1. Sorry, guys. I'm going to put my 1. Same thing like I know. So I put 1 over here. It doesn't make any difference. You want to put 0, absolutely right. Problem. I put 1, so I will stay with 1. Okay, do you see what I'm saying? That's not a big deal. So now, what else do I have to fix? So what else do I have to fix? Right, the first one has to be flipped like we had before, so we'll still continue with this. Now, just in case if you felt like you got lost, we had to split the integral because it doesn't fit into the theorem. When we do this, we pick a number, and it really doesn't make a difference what number we pick. We put 1. Then also, we have to flip the upper and lower limits into the first integral for the first integral because, again, the problem with the theorem. So this will be negative 1 to square root of x arctangent of t dt and plus integral from 1 to 2x arctangent of t dt. And if you paid attention, all of this still not this, right? You were just modifying function. You're trying to fit this with a theorem. Well, now you can take the derivative. So, taking derivative of we have f prime of x. What do we do with the first one? We're going to what? Substitute square root of x, right, into the function. But since this is not just x, right, we will what? Take the derivative. So it's 1 over what? 2 square root of x. Good. So that's for the first one. Okay, so this is for the first one. Then moving to the next one, we're going to put plus. So we have arc tangent of what? 2x, good. And then times by 2. And you're done. Okay, now let's rearrange this, but I'm not saying you have to find LCD. That's fine. So I'm going to keep positive first, so I have 2 arctangent of 2x minus arctangent of square root of x over 2 square root of x. So that's it. Alright? So take a look at that number 5. Get the idea what you have to do. Then maybe you have to split the integral. Then maybe you have to flip. And then just a normal thing. So you have 2 problems similar to this on your next exam. So you should not miss this. It's very easy.
Will they involve tricks too?
But what happened here? Did you really use any trick for number 5?
No, but
Okay, just don't like how arctangent looks like. Put tangent with the negative 1. It's the same, right?
yeah.
Okay, it doesn't make any difference. So this is not a difficult problem. Just get the idea that you have to modify maybe, and you have to substitute and take the derivative of the upper limit, right? Okay, so that's it. So that's about the first theorem. And again, let me refresh what happened with this first theorem. Well, the first theorem connected derivative with the integral. Okay, and basically what we said that that was the antiderivative. And now if we go to the second theorem, that's where we will learn how to find integrals. So, the second theorem says this. If f is continuous on closed interval AB, then, and now let's pay attention to what's going to happen right now, it's important. Then, integral from A to B, so what's happening right now? This will be what kind of integral? It's a definite integral, right? It's no from A to B. Now, I know I didn't finish writing this, but we talk about definite. That means what do you get as the answer? A number, not a function, okay? Then integral from a to b f of x dx equals this. And that's where the key, okay, we have, equals to this. F capital of b minus f capital of a. And now let's explain what that is, okay? Where f is capital, f capital, is any antiderivative of lowercase f such that f capital prime equals lowercase f. Okay? So let's take a look what we actually have to do in order to find definite integral. So in simple terms, again, it can be more complicated, but in simple terms, you want to make sure that this one is continuous. We'll talk about this more later, but right now you want to make sure this one is continuous. When this one is discontinuous, then this theorem doesn't work. You understand that? You cannot find integral if it's discontinuous. Normally we will say it does not exist, okay? But in Calc 2, there will be more revealed to you if it really exists or doesn't exist, okay? But right now it doesn't exist. And then, what does it say here? It says that this capital F is what? Antiderivative of what? Lowercase. So in order for you to find integral, now using calculus procedure, okay, or algebraic procedure, you need to know the antiderivative of f of x. That's all you need to know, just antiderivative. And then when you find this antiderivative, you will substitute v into it, and when you subtract, what do you do next? Use again the same antiderivative and substitute what? A. Okay? That's the formula that we're using. I don't know if you can call this formula, but that's the concept that we have. So, using some information from the first theorem, applying it here, talking about antiderivatives, now theoretically, in most of it, let's say, what, 99.9%, we can just do it and use this concept to find the integral. So let's take a look at example. So this would be example what? 6?
Yeah.
Alright, so let's find integral from 0 to 1. So this one is what? Definite. And please again, make sure you understand the questions. You're getting so many problems and almost every single one has different question, okay? So here, it will say evaluate the integral. It's not going to say find the derivative like before. Understand that? We're not looking for any derivatives here. And it's x squared dx. Well, you know what the answer is, right? What's the answer? What's the integral from 0 to 1 of x squared dx? Yeah, it's 1/3. We had this yesterday, okay? But now let's use the procedure actually without those things like you should know or using special form. So, what is the theorem saying? F, which is what? X squared, right? Must be continuous on this interval. Is it?
Yeah.
Right? Just simple polynomial. Domain is all real numbers, so it's continuous. The next step, what I have to do? I have to find what? Antiderivative of what? X squared. What is the antiderivative of x squared?
X cubed over 3.
Right? And I'm showing you now how we do this, okay? We're writing the procedure right now, so please follow me. So you know it's x cubed over 3. So you write like this.
Baseball players.
X
There's a
cubed
mandatory baseball meeting Wednesday,
over
November
3.
7th after school.
And
It's
then you
baseball.
put a bracket over here.
Gen Ed 101. Brooke Players will be teaching Gen Ed 101
And then you
through
say
CSI during
0
second semester.
and 1.
She has 5 available seats open.
So what we're doing here, we're just simple saying, okay, I know what antiderivative
Yeah, everyone
is.
in the spirit of
And
Thanksgiving.
antiderivative is x cubed over 3. And what do I have to do next? According to the theory, I have to
This will
substitute
start next Monday, November
1
12th.
into this antiderivative and then subtract 1. Substituting 0 0 into this antiderivative. But we always put this step before you actually substitute. Please do not substitute before you, I can call it declare, say what the antiderivative is. So when we substitute right now, what do we get? We get 1 cubed, right, substituting 1 over
Applications will be due by
minus
November 9th.
0 cubed over 3, and you can skip this if you don't want to show you how to substitute. Okay? And the answer is what?
Discussing the Caring and Sharing Festival and the Christmas Council food drive. If you cannot make it, stop by to see Mrs. Gardner.
So this goes much faster as what we did in section 5.1. Remember, I had to go through the limit, and the sum, and get all those pieces together, and then apply the limit, and I'll get my 1/3.
And that's all.
This is practical multiplication.
Well, it's not the another equation, it's the process how we do it. So we always have to show this. X squared, antiderivative is x cubed over 3, you put bracket 0, 1, and then you substitute. You always have to show antiderivative. Okay? Always have to show what you have, and then you only substitute.
Do you need to have constant plus c?
No. Why would you need plus c? Because this one is what kind of integral? Starts with d. Definite. So we can get plus c only if it's indefinite. It will be on Friday. Okay? Because right now you're actually looking for the area, exact area, right? Under the curve. But you will get c, don't worry, we're not going to leave that alone. You will get some examples where you have to say plus c, but it's not today. It will be on Friday. Okay? So let's do one more and we'll finish. So, 7, for example, and it kind of will be similar. Let's say I have from 2 to 4, and I have square root of t dt. Okay? So, well, first of all, square root of t, or square root of x, right? Is it continuous on this interval from 2 to 4?
Yes.
Yes. All right. So we have no problem. We continue to do it. So to make this easier, we're going to change the square root of t to 1 over 2 dt. Then we need to find what the antiderivative for t to 1 over 2 is. So what is antiderivative of t to 1 over 2?
2/3 t to 3 over 2.
Right. Okay, now I'm going to go slow right now. Okay, you can write the answer. That was the right answer. But overall, what do we have? We're going to add 1, right? And divide by whatever we get. So if you add 1, you get t to 3 over 2. You add 1. And then you have to divide by 3 over 2, right? The whole fact. It says x to n plus 1 over n plus 1, right? And then we have this from 2 to 4. But you know what this is. If you simplify, that will be what? 2 2/3, yes, no? Okay. So you already said 2 over 3, and we get a t to 3 halves, and then you go from 2 to 2. Do you understand? Now remember, I'm showing you the concept. I'm not saying, well, that's all you get. But your goal is to see that antiderivative, and it's actually section 4.9 from the previous chapter, where you have to both maybe modify your function with it, and you have to look at parentheses, you want to get to all the maxes and powers. Okay? But right now what we're going to do, we're going to substitute 4, and substitute 2. So we have 2 over 3 times by 4 to 3 halves minus 2 over 3 times by 2 to 3 halves. Now you can leave it like this, and also you can give decimals, unless it says give decimals. So we really have to simplify. So tell me what we get for the first fraction. And you can use your calculator, I really don't care. You can show me manually work here. So what do you get over here?
mom to make sure she only used the one, and then she said she sold one more.
Your mom sold for more. Your mom said she had first.
Yeah, so that'd be 16.
Let's get together too.
Then subtract. And what do we get here? It's a little bit more complicated. So this will be, say again. Okay, that's right, let me go slow.
Mr. Heatley, please stay on the office. Mr. Heatley, please stay on the office.
Yep.
Good work. They are the same
Got all
base.
these kids. I'm gonna be late.
So we will have 2, 5 halves, right? Over 3.
1, 2.
And this will be
Why are you
16
shaking?
over 3 minus.
outside. Was that what I'm
32.
You're giving me hypothermia. 2, 3, 4, 5, 6, 7.
Then we have 16 over 3 minus 4 square root of 2 over 3. And again, why is it 4 square root of 2? Because 32 is 16 times 2. And the final answer will be with 1 denominator. So we get 16 minus 4 square root 2. And this is the final answer. So we may have a little hard time actually to simplify some answers when we're trying to finish the problem. There will be some, difficulties. Actually, those 2 areas where we can have a problem. But then the second problem we can have, which is actually go back to the very last final answer. Okay. So we will continue next time. We'll continue next time. And
Did they just say that?
They call the office.
got the exam, so today I will finish grading them. Okay. And tomorrow I'll listen to you.
Never won my class.
And this is just a general statement to all of you. I don't know if you're checking your email, but I think yesterday